Jayalakshmi is there?
Yes, sir. Yes, I am here. Shall
Yeah,
we
yeah.
start, sir?
Yeah, we can start, I think.
Yes.
Okay. Good evening, all. A warm welcome to all the participants to the second meeting of the webinar series themed as Macromolecular Lecturing, organized by the Society for Polymer Science India, Thiruvananthapuram chapter. The Society for Polymer Science India is one of the premier professional societies of the country, formed with the intention of promoting advancement in the field of polymer science and technology. Thiruvananthapuram chapter of the Society for Polymer Science India was formally formed on January 20th, 1996 with an aim to provide a forum for interaction among the polymer scientists, engineers and technologists in the R&D laboratories, universities and industries across the country. The chapter has been deemed as one of the most vibrant one with handful of events like seminars, invited talks and charity programs which are being organized regularly. With that said, we start the session by inviting Professor Kuruvula Joseph, President, SPSI Thiruvananthapuram chapter, to welcome the speaker and participants. Sir, please.
Yeah, thank you very much. Good evening to all. I'm extremely happy to join this program. This is our second macro lecture. You know that last month we initiated this program with the talk of Professor Sadhan from Akron University, USA. Today we have Professor Fernando Gomez, my close friend and a collaborator. You know, he is from Federal University of Rio de Janeiro, a wonderful researcher who is working on various areas. A major focus on polymer-based composites, materials, cement, bio-based materials, nano systems, and things like that. You know, Professor Fernando is from one of the best laboratories in South America. COPE and the Federal University of Rio de Janeiro. They have wonderful facilities, laboratories, excellent researchers. I visited several times, stayed there. And in fact, when I visited in 2018 or 19, I really got amazed by seeing their science park. So the concept about science park totally changed by seeing the science park of UFRJ. So many hectares of land, various industries in collaboration with the university, department and research centers established the park, startups. And it is really amazing. In fact, I requested Professor Fernando to show some of the parks, some photos and something about that park also. And he's a very, very, you know, dynamic researcher working in various areas. And today he is going to talk on polyaniline, a key ICP for improving properties of sensing materials and for foreseeing trends. A very interesting topic where he is currently working on that area. And all of us are working on the similar areas, and it may be useful for us as well as the beginners. On behalf of all, let me extend a warm welcome to Professor Fernando Gomez to this function, as well as also to deliver the lecture. I also wish to welcome one and all. I can see Kannan sir and all others, all senior colleagues, and my fellow SPS members, MRS members, students, a lot of people are there. And I know that some are having some connectivity issue. Hope that they will resolve it and join. one word, let me extend a warm welcome to all for this function, because it's a very interesting talk. And as you know, Rio is a wonderful place. And though I have visited many places, one of the interesting place is Rio. Beautiful place, very nice people, very good food, especially seafood. And all of you should, in fact, one should go and see Rio at least once in a while. With this, I once again welcome Professor Fernando Gomes. Muito obrigado, meu filho, meu amigo.
Muito obrigado.
Obrigado. Thank you.
Thank you so much.
Thank you, sir. An important announcement. Dear participants, you are requested to follow some instructions. All are requested to mute the microphone during the session. Interactive session is planned after the talk. The questions can be posted in the chat box, or you may also interact with the speaker in the allotted time. Feedback form link will be posted in the chat box towards the end of the sessions. Participants are requested to fill the same. With that said, may I now invite Dr. Benike George, Group Director, Analytical Spectroscopic and Ceramic Group, Vikram Sarabhai Space Center, and Executive Committee Member, SPSI Thiruvananthapuram Chapter, to introduce our speaker of the day, Professor Fernando Gomes, Federal University of Rio de Janeiro, UFRJ, Brazil. Over to you, sir.
Thank you, Dr. Jayalakshmi, and a very good evening to Professor Fernando, Professor Kuribula, and all members of SPSI Thiruvananthapuram chapter. So without wasting much of a time, let me go to the assigned task of introducing the speaker. Professor Kuribula has already talked about Professor Fernando Gomes. Professor Gomes is a graduate in chemistry from the University of Espírito Santo, and he took his graduation in 1999, his master's in 2002, and PhD in Polymer Science and Technology from the Federal University of Rio de Janeiro in 2006. Postdoctorate in Experimental Design by Chemical Engineering program at COPE UFRJ. He is currently professor at the Institute of Macromolecules at UFRJ and full professor of the Nanotechnology Engineering program since 2019. Young scientist of the state of Rio de Janeiro, scientist of the state of Rio de Janeiro, received the chair professorship of Nanoscience and Nanotechnology from Mahatma Gandhi University in 2018. He is a member of editorial board of many prestigious journals, including Current and Applied Polymer Science, editor-in-chief of the same journal, associated editor of Medcraw online journal, Polymer Science since 2017, honorable editor of Academic Journal of Polymer Science, and member of editorial board of Composite Interfaces. He founded a Brazilian Journal of Experimental Design, Data Analysis, and Interfacial Statistics in 2021, and is its founding editor-in-chief. He works mainly with the polymeric nanocomposites obtained from renewable energy sources in three main areas: in the field of environmental recovery, coordinating research projects focused on the use of renewable sources for the removal of oil spills in the field of human health, coordinating projects that seek kinetic and spatial control of the drug release in process, and in the field of sensors, where he coordinates projects that seek to obtain plant fibers conducting electricity and their use in sensors for intelligent devices. As a distinguished scholar, he has more than 150 publications in international journals and 9 book chapters and 1 book to his credit. With this small introduction, let me invite Professor Fernando Gomes to deliver his lecture. Over to Professor Gomes.
Thank you all. Thank you so much. It was very nice. Heard such beautiful words from you. First of all, I always like to say that I am a very shy guy. So please take your time, do your questions. You can interrupt me. There is no problem at all. Okay. And today, well, first of all, good evening. It's a pleasure to be here talking to you. I love Kerala. I spent very, very good times in this place, and I have good friends from Mahatma Gandhi University. So it's a real pleasure to be here today. Okay. I'm trying to talk a little bit about a passion of my life. I'm really in love for this polymer, polyaniline. This is such material. It is so nice to work with it. And I will try to show you some of the applications and the use we are using polyaniline in my lab. Okay. So this work has been developed in the Federal University of the Rio de Janeiro. Here we have some pictures of our beautiful city. More specifically, this work is developed in the Fundão campus, is this island in the right corner of this slide. Mostly in the Macromolecules Institute, which was founded by Professor Luisa Mano. In that place, I am the head of the Biopolymers and Sensors Lab. We have a vision. We like to think about using polymers in service of the environment and quality of life. And our mission is to move forward the use of natural resources seeking new properties and applications. I don't know if you used to work using natural resources, but we have a problem. Wow, and it is related with the costs of these materials. We can imagine that any kind of macromolecule we are trying to prepare using natural resources will be at least 25% more expensive than the analogs from petrochemical industry. So we have a challenge. Somehow we must improve the quality and the applications of these materials, trying to spread the use of these materials. So in my lab, we deal with synthesis, the chemical modifications, and the preparation of nanocomposites. And to my mind, the preparation of nanocomposites is the best way to improve and impart new properties to these materials. And when we do this, we can use this kind of natural resource or natural macromolecule in several applications, such as environmental recovery, drug delivery, sensors, and so on. Okay, most of the time, people ask me to talk about environmental recovery because I believe that maybe 90% of my students are in love with this kind of subject. And nanocomposites are very, very useful in this kind of situation when we are trying to remove oil from the water and so on. Drug delivery is also, well, a kind of very exploited research line. And sensors, I don't know why, maybe because the little bit of mathematics we must deal with. I imagine that 1% of my students faces this kind of challenge. But when we think about sensors, wow, we have a lot of considerations to perform, such as this is a very, very impressive field of research, and the developments in this field are so fast that we must study every day about this subject to understand what is going on in this context. Okay, more than this, sensors are around us, so we can find several kinds of sensors, and among them, I will talk a little bit about the production of pressure, gas, and magnetic sensors. Okay, the sensors markets, as we can see, these markets are expanding, and the pressure one is one of the most promising. But okay, let's talk about the projections regarding the gas sensor market. As you can see, we are talking about $1.5 billion by 2026, while in the case of the global magnetic sensor market, we are talking about $6.2 billion by 2025. And the most impressive is the global pressure sensor market, which is around $21 billion by 2025. These materials and these devices always are useful, and they always are being researched, trying to improve them, besides decrease the price. So when we think about polyaniline, this is perfect because it is a very, very impressive material with very good properties and low costs. So this is the why polyaniline. So as we know, PANI is the oldest and most studied conductive polymer in the world. It was reported the first time by Letteby in 1862. This polymer presents a very, very good electrical conductivity. The easiness of preparation is amazing. When we try to prepare PANI, it's almost impossible. It go in a wrong way. It's very, very nice, very easy to be prepared. Besides it, we have also the very good stability to heat and to air, and as I said, the low production costs. But we must face some drawbacks. Among them, we have the problem related with the poor solubility of this polymer in common organic solvents. Besides this, we have the poor compatibility of polyaniline with the common polymer materials, which lead us to the poor processability of these blends. So most of the time we will work using polyaniline in blended materials or modifying substrates. This second way is very nice because when we modify some substrates, we are using a very small amount of polyaniline, and it is so good as I will show you in the next slides. Okay, let's talk a little bit about gas sensing. When we are thinking about gas sensors, we are talking about one of the most important devices, mainly when we are thinking to detect noxious gases, which is very, very important in several industries, such as mining, the petrochemical one, and so on. In our case, I am going to show you a sensor which was designed to deal with acid vapors. So the objective of this work was the production of materials based on cellulose modified with PANI. These materials present color changes in the presence of sulfuric acid. And we can follow the color changes according to the protonation degree of the polyaniline. And now we have a paradigm shift. Let me try to explain. Okay, this paradigm shift is related with an expressive reduction of the used amount of PANI. For instance, when we use it to work preparing blends, most of the time we needed around 20% of PANI inside a conventional polymer to prepare our sensing materials. When we start the modification of these substrates, for instance, the cellulose, we start working with less than 1% of polyaniline in a dispersion to perform this kind of modification. So we are using a very, very low amount of this conducting polymer, and this very low amount imparts in very interesting and new properties. Here we have some examples. In the left corner of this slide, we can see the cellulose modified with nano polyaniline. And as we can see, this modification can be easily proved by the change of the color of the material. We have the cellulose is yellowish, and when we modify with the nanopani, it becomes greenish. Okay, but let's try to see it closely. To do this, we use the electron microscope, and as you can see here, there is no difference among the pictures we are showing here, because the amount of PANI on this surface is very, very small, as I said. We are talking about 130 micrograms per square centimeters. So it's almost impossible to be seen in this kind of surface. But when you use a small angle Xray scattering, we can understand a little bit more about the structure of these nanoparticles. So when we look to this plot in the left corner of this slide, as we can see, PANI presents 3 scattering peaks, and by Gaussian deconvolution, we can prove the cellulose modified present also 3 scattering peaks. Okay, these 3 scattering peaks are related with 3 types of orderly conducting island in these materials. So we can calculate the size of these islands, and here we have the average diameters of them. In green, the ones from the polyaniline, and in red, the ones from the polyaniline on the celluloids. As we can see, the largest one in average is around 110 nanometers. And it's very nice because when we compare the results from SACS with the results obtained from AFM, we can prove that statistically the particles we perceived in AFM possess the same diameter of the particles observed using the small angle X-ray scattering. We also use the UV-vis spectroscopy, and as we can see here in the left corner of this slide, there are 3 absorption peaks. They are placed around 370 nanometers. This one, 450 nanometers, this another, and 780 nanometers, this one. There is a very simple calculation we can perform, which is the calculation of the rate between this band and this another band. When we do this, the result is equal to 1.75. And according to the literature, this result proves us that this punny is doped. Okay, so it is in the conducting form. Here in the right corner of this slide, we have the FTIR, and it seems to show the characteristic bands of the punny. It's a little bit hard to say. In that time, we used to study this spectrum. How can I say? With eye inspection, looking for the bands. But now we are using very easy to be performed statistical technique based on the root mean squared error. And it's very nice because using this, now we can prove there is punny on the surface of these fibers. But okay, at that time, we didn't know how to use this kind of technique. In this slide, we have the X-ray photoelectron spectroscopy results of these materials. In the left corner, we have the punny, and in the right corner, the cellulose modified with punny. As we can see, there are 2 protonated nitrogens in both cases, and it is very nice to us because it is showing that before the modification, we have 2 kind of protonated nitrogens, and after the modification of the cellulose, these 2 protonated nitrogen were preserved. So we can imagine that punny on the surface will work. as we are expecting. And here finally we have the test we performed to determine the concentration of the sulfuric acid on these modified substrates. Okay, this test was performed using sulfuric acid vapors, okay, which were dispersed in a chamber, and then these small sensors pieces were put inside this chamber, and we monitored the amount in ppm of this sulfuric acid inside this chamber. Then, after a small time of exposition, we removed this celluloids, this modified celluloids, and we used a scanner, sometimes a camera. So we took pictures of these materials, and we studied the RGB of them. Okay, when we did that, so we perceived that between 25 and 500 ppm, this material is able to detect the variation of the concentration of the sulfuric acid by changing colors. Among them, the blue and the red channels are the best. So we use these two channels to follow the changing of the concentration of sulfuric acid in this case. Regarding the magnetic sensing, when we are thinking about magnetic sensing or sensors, we must think that they are often used for secret and military applications, such as detection, the localization of ferromagnetic or conducting objects. So it's a very, very interesting field. Our first work related with this subject was performed modifying the surface of magnetic nanoparticles. In this specific case, we used magnetite, which was modified with PANI. Here we have the AFM of this sample. And then we studied this material in the presence of a magnetic field and without a magnetic field. Here, as you can see, we have the surface resistivity of this material without the magnetic field. So we have an average result around 390 on centimeters. Okay. Then, under a magnetic field, around 200 Gauss, the surface resistivity dropped from 390 to 235 on centimeters. It is around 165% of increase of the electrical conductivity. It is a very, very nice result. Okay, but here we are using basically only the PANI. Now, thinking a little bit more this kind of magnetic sensors, we proposed to use mango fibers modified with punning. Only punning. Okay. So we produce mango fibers, which were modified with punning. And these fibers, after the modification, presented magnetic force. Okay. Here we have the mango fibers, the surface of these mango fibers, which were studied using electron microscopy. And it's interesting to see that first of all, we clean up these fibers using hydrogen peroxide, and it was very effective to remove any celluloids and lignin from these fibers. But the shape of the fibers remain the same. Here, and here. This last one is the fiber after the modification with punning. And as we can see, the shape of this fiber is different from the others. Okay, why? Because these fibers were treated in this media during 3.5 hours. So the acid in the polymerization medium was responsible for this surface degradation we are seeing here. Despite that, they presented similar thermal stability, with all of them were stable up to 250 Celsius degrees. And here, in the beginning of these TGA curves, we can see a loss of weight related with water. Okay, so when we think about this specific range of temperature, we can try to extract more data from the DTA. So in the right corner of this picture, we can see these three peaks related with the enthalpy of this loss of water. And it's very interesting because, as you can see, the peak related with the material modified with punning is the smallest among all of them. Okay, so it is proving to us that this surface, after the modification with punning, is more hydrophobic, proving the surface modification. Then we studied the volume resistivity of these materials. So in the left corner of this slide, we have the electrical resistivity. For a comparison, the electrical resistivity of the mango fibers without the treatment is around 300 mega ohm. After the treatment, for 3.5 hours in the presence of the punny nanoparticles, the volume resistivity dropped to around 3 kilo ohms centimeter. So the modified material is 110,000 times more conductive than the mango fibers. Okay, then we try to explain these numbers. Some how can I say, some undergraduate students we had in our lab in this time. And then we used this strategy which is basically we use these modified fibers as a kind of no resistance, electrical resistance, and we used it inside this lead. And then here we can see in the first case the lead, when you use a small piece of this mango fibers modified with polymer. No. In this first case, only the mango fibers. Then the mango fibers modified during 1 hour. No, sorry. This is the raw material. The fibers modified 0, 1, 1.5, and 3.5 hours. And then we can see that after 1.5 hours, this material is conducting electricity. And about the magnetic properties, we did this kind of homemade system. We prepared it. It was developed in 2013, and it is a homemade device when we can do our magnetic force test. Okay, so we have an electromagnetic, a voltage source, an amperimeter, a Gaussmer, a sample holder, this one here, and an analytical scale. It's very, very simple to be prepared, and you can look for more information in this paper I am showing here. So, using this homemade device, we could measure the magnetic force of these materials. Okay, here we have a paramagnetic cobalt salt. As you can see, there is no relevant magnetic force response. Even using a very high magnetic fields, such as 900 Gauss, while when we are talking about the nanomodified mango fibers, we can see that after around 350, 375 Gauss, the magnetic force response start to increase linearly. So it proved to us that these fibers were modified and that they are working as a material which possess magnetic properties. And these magnetic properties are related with the presence of polarons inside this conducting polymer in its protonated form. Finally, the pressure sensing. Pressure sensors are used for many, in many situations, automobile, medical, and so on, directly. And we also can think about the indirect use of this kind of pressures. In such case, measuring the speed of some flow or gas, water level, altitude, and so on. So they are very useful. In this case, our main objective is the preparation of sensing materials using green composites. We perform this not modifying the substrates. In this case, we prepared a blended material. This blend was prepared using cardanol formol and cardanol furfural resins. In both of them, we inserted different amounts of PANI, and then we deal with this, trying to understand what was going on with the physical properties of these materials. So, one of the first works related with this was this one, the mechanical percolation of PANI particles in substrate, which was cardanol furfural resin. Here we have some results. In the left corner, we have the FTIR. This spectra show us the PANI characteristic bands, while in the right corner of this slide, we are seeing the wide-angle X-ray scattering, which is more useful to us in this case because, as we can see here, we have the cardanol furfural and the blends with different amounts of PANI. In this case, 20% of PANI, and here the PANI. Okay, so looking at this result, we can understand that in this blended material, there is a kind of phase which is from the PANI. Okay, so we can imagine that this dispersed phase, this dispersed PANI crystalline phase, will be useful to the percolation under pressure. And these sensors, in this case where we are talking about pressure sensors using conducting blends, they work following this kind of percolation. So when you press this kind of material, you are putting all these small conducting crystals closer, which increase the electrical conductivity. Okay. So here we have some results related with the use of different pressures on the change of the electrical conductivity. And as we can see, the most sensitive materials are the ones filled with 5 and 10% of PANI. Okay, but we need to see the diffraction peaks. So the further steps of this work were performed using this one filled with 20% of PANI. Why? Because the idea was we were interested in understand how the PANI structure would change under pressure. Okay, and to do this, the wax measurements under pressure were only possible because of this professor from my former university, Professor Marcos de Azeredo. Professor Marcos de Azeredo prepared this amazing pressure cell, and this pressure cell is invisible to the X-rays. So here in the middle of the cell, we put our sample. All this cell was compressed, and then we passed through it X-rays. Okay. Then where is the next? Wait a minute. No. Here. Okay. Here, the obtained results were treated via Gaussian deconvolution, and it was very, very nice because we could separate all the crystalline contributions, and then we proved that all these crystalline directions were preserved, but the Z1 was shrinking. Wow, it was very nice. It was very nice. So we saw in line in situ it take place. We could see this cell being compressed. Okay, most of the time we use this kind of experimental device. This one was developed during my PhD, and it's, to my mind at least, it is very interesting because the idea was in that time, 2005, the idea where we must pair this electrometer and an instrument machine. Wow, it was very, very hard to be done because in that time we used 3 computers to do this. Wow, it's a shame. More than this, when we think about the code wrote to acquire and process these signals, well, it was huge. For instance, it was written using BASIC, and for instance, a single integration step needed about 150 lines in BASIC to be performed. Nowadays, we are doing the same thing using Python now, and from, I don't know, the number of lines of code, we are today maybe using 15 to do the same work. Okay, so try to take a look in this in Python. It is very, very good. Up to now, this method is still being used, as we can see here in the work from Lopes and another one from France. Okay, and I am very glad with this because it was my first publication. But now we must think about a little bit about trends and perspectives, because this is my talk today. Okay, so we know PANI was firstly reported in 1862. Okay, but what is going on with this subject? How can we take an overview related with new research and what people, how can I say, is researching regarding this subject? Okay, one of the ways to deal with this kind of questions is through the data mining. So why we must think about data mining? For instance, the Brazilian government pays around $110 million per year to allow us to have access to these papers. So we shall use it. Okay, so here we have first paper published in the Brazilian Journal of Experimental Design, Data Analysis and Inferential Statistics. Well, it was maybe the best result from the first Brazilian conference on experimental design and data analysis. And as you can see, we have this challenge, and there's no way. We are trying to do our best, but there is no way to work without the publication charts. But to our minds, the idea is we are working with the lowest article processing charge we can support. So we have different prices. When the first author is graduated or postgraduate, we are using this charge, $33. Undergraduate, being the first author, it drops to 21. If the first author is from high school, $10. And if the first author is from the elementary school, $0. The charge is en masse. Why we are thinking about elementary school? Because here in Brazil we have some fellowships to this level. So a very, very small amount of elementary school children, they have access to the college facilities to perform some initial research. It is very nice. It is very nice. Okay, but this paper started from a statement from Professor McDermott when he was here in Brazil attending the Macro UPAC 2006. That time he told us, I am sure there is still much to be studied about polyaniline. Wow. And it was wow, so strong in my mind. Okay. And I embraced this challenge up to now. So the idea was, how can we use this statement from Professor McDermott to understand what is going on with this hot theme, PANI, in the last 20 years. Okay, so we use text mining, and we did it trying to understand how this theme has evolved during this period. Besides, we also try to extrapolate scenarios for the coming years. How we did it? So, first, we used the Science Direct. From Science Direct, we gathered 341 papers, scientific articles containing the word polyaniline from 1999 to 2019. Okay, so we split the titles and the abstracts, and we used few tools which are easily available in the internet. First, we used the library of Calc and Writer. We used the word cloud, the textalizer, and the Voyant tools. Okay, the first result is from the word clouds of the titles. And as we can see here, well, we have three most prominent words, which are polyaniline, synthesis, and composites from the titles. From the abstracts, it is a little bit different. We have polyaniline, high properties or conductivity, and composites. Okay, but when we are looking at this kind of picture, oh, they are interesting, but how can we understand which terms are really the most relevant among all of them? So the idea is change the tool. And here we are now using the textalizer, and this first table shows us the most cited words, and it is easy to be understand to understand how which of them are most relevant. Polyaniline, of course, is the main word. Synthesis, composites, and so on. While among the abstracts, again, polyaniline, high, composite, electrochemical, and so on. Despite this, we need to use a third tool. It was the Voyant one, because the Voyant provides us information regarding the correlations between terms. So here we have a table from the Voyant, and this table shows us the correlation results. We fixed one term, which was the polyaniline, and then we allow to vary a second term. And here we saw that the highest correlations are between poly and conducting, or poly and films, when we are thinking about the titles. Regarding the abstracts, poly and nano, in this case nanofibers. Well, and it's very relevant because despite this correlation is lower than this one, the number of words here is larger, much larger than the words here in the titles. Okay, using the Voyant is very nice because all of these calculations are preserved in this corpus. As you can see, all of these corpus are available in the Voyant Tools site. So anyone can access it and use this data. And here we have the final result from the Voyant. And this picture is showing us the trends of the main terms from combined titles and abstracts between the range researched. Okay, so here in the Abscissa we have the corpus, all of them, since 1999 up to 2019. And here in the ordinate, we have the relative frequencies. Take a look at this arrow this arrow is related with the most prominent term, polyaniline. Okay, and as we can see, the highest relative frequency over most of the analysis time are from this term. And it's very interesting to see that this frequency is dropping. Why? Because these studies are being more and more focused on improve the properties of the pony. So they are always being performed in an association with another blend, another word such as blend, composite, or nano, and so on. On the other hand, when we take a look at the second most frequent word, nano, well, it's very interesting because, as we can see, nano is gaining relevance over the years. This rise is the result of the ability of the nanoparticles, nanostructures, in modifying the properties of the host materials. Wow! So, if we are thinking about how this subject, pony, will evolve, we must think about using nanoparticles, nano, inside this matrix. Okay, but we can improve this kind of research. And now I'm showing to you a study. It was also submitted to BGDIS, and it was part of the last class of data analysis I offered to my graduated students. So during this course, I've proposed a challenge. The idea was related with we should try to discover which nanofibers most improve the electrical properties of pony. To do this, we should answer this question. Literally, do nanoparticles improve polyaniline electrical conductive or electrical resistive? Okay, then we did it. How we did it? Well, this time we used the Scopus database. And it's very nice to work using Scopus because we can download a lot of papers every time. So it's very nice. Okay. We gathered 30,780 documents from Scopus. From these documents, the ones from these 2 years, 2021 and 2022, were excluded because these years are still receiving new works. So titles and abstracts were saved as RIS files, and they were analyzed using Voice Viewer software. Okay. Then, after this first analysis, we understand that we must use a more elaborated search key, which was the first one was only polyaniline. The second one was nano and PANI and improve and electrical conductive or electrical resistivity. And we focused only on the scientific articles. This time, our research allow us to retrieve 392 documents from Scopus. These documents, we used them to perform a data extraction and then a meta-analysis. This first result show us how the number of papers, scientific papers, is increasing during the years, only related with PANI. As we can see, there is a very strong determination coefficient related with this function, and it shows us that this topic PANI is being researched in an accelerated way since the 80s. Okay, and here we have the results from the Voz Viewer. As we can see here, Voz Viewer is a kind of artificial intelligence tool. It works producing clusters, so it's a classification tool. And as we can see here, we have three main clusters. The first one of them is this one in red, which is related with characterization techniques. The second one is in blue, and the most relevant node is this one, the carbon nanotubes, while the third one is dominated by this node, performance. The third one is this green. Okay, but here we can see two nanofillers. The first one is the carbon nanotubes, and the second one, graphene. And when you use this another kind of representation, here we are using an overlay map. Well, this overlay map, take a look. Here in this bar, we are seeing the average years where all of these terms are being presented. So in the right corner of this bar, we are seeing the red color, and the nodes in red are the most are the newest. Okay, while the nodes in blue are the oldest. Perfect. When we see it, it's very interesting to perceive that carbon nanotubes are around 2015, 16, and graphene is a more modern term, which is around 2016 and 17. Okay, so among these two, this is the newer. Okay, but now we have two new keywords. So we use the third search key. This one was equal to the second one, but we used two additional keywords, graphene and carbon nanotube. Okay, this time we gathered 177 documents from Scopus, and all of these documents were downloaded. So we opened one by one looking for scratching relevant statistical information. It is interesting, but highly disturbing, because from this 107 documents, only 15 presented useful data for the proposed meta-analysis. Wow, less than 10%. We must think about it. Okay, here we have the results from these 15 papers. In some cases, such as this one from Shaw and collaborators, they presented inside this single papers four sets of results which were useful to our study, using carbon nanotubes and graphene. So we use it all. Okay. So these results were treated using a meta-analysis tool. And here we have the forest plot of all of those results. Okay, and as we can see, this forest plot is very interesting, and it's nice because people from humanities and medicine and so on are used to do this kind of study, while we aren't. So at least to my mind, it was a novelty. Okay, so when we are looking at all this data, we can see that there is this small bars here with this point inside of them, and the size of this point is related with the relevance of this study. Besides, if this error bar passed through the zero, it shows us that this set of results in particular are statistically relevant, okay? But this diamond in the bottom of this picture is the key. Wow, when we are looking at this diamond, we can see that it is in the positive corner of this range. So the presence of these nanofillers is improving the electrical conductivity of PANI. And more than this, we can also see that the length of this error bar does not pass through the zero. So these results are statistically relevant. Therefore, we answered this question, which particles are improving the electrical conductivity of PANI, graphene and carbon nanotubes. Okay, as a quick summary, from the forest plot, the model effect is positive and non-zero. Okay, so the meta-analysis proved that the nanofillers in this study increased the conductivity of PANI. Therefore, graphene and carbon nanotubes should be prioritized in future works involving PANI until new evidence suggests the use of different nanofillers. So if you are thinking about PANI, try to use carbon nanotubes or graphene to improve the properties of your material. And as remarkable points, PANI must be more and more researched. PANI-based nanocomposites is a key material to achieve new and improved properties, improve our society way of life when we are thinking about the sensors, besides reducing cost of new device. People, this is a multidisciplinary subject, okay? So we only can do a good research in a cooperative mode. And please, we must improve data from our research. We must use statistics, and we also should offer an easy way to other researchers to get access to our data. Let's do this, it will improve our science. Wow, this is my message. Again, thank you all so much. Thank you, special thank you to the Society of Polymer Science India. A special thank you to Professor Coruvilla Joseph. Wow, thank you so much, Professor, for this kind invitation. Thank you all.